In this lecture, we continue to discuss on Prandtl's lifting line theory. So, in the previous lecture, we had discussed about the trailing vortex sheet, a continuous distribution of gamma along the lifting line, which was proposed by Prandtl, and then based on this model, he finally came up with the lifting line theory. So, let us take this concept forward. We recall dw equal to minus d gamma dy into dy by 4 pi y naught minus y. This was the expression we derived for the downwash. Now, if you integrate along the entire lifting line covering the entire span of the wing, then you will have the total value of W at y naught. This is the expression. As I already said, that when you are looking at any one particular element of the trailing vortex sheet, then you have to be very careful about what the location of that trailing vortex line is and what is the location of y naught. So, if this is having a counterclockwise movement, then any point to its right will see an upwash, any point to its left will see a downwash. So, this has to be kept in mind clearly. Now, we recall about the induced angle of attack, which we discussed in one of our previous lectures on finite wings. So, the induced angle of attack, we indicated it as alpha I, and you may recall that that can be given by tan inverse minus W y naught by u infinity. And we assume alpha is small, and if you do so, then alpha I at y naught will be given by this expression. We remember that the geometric angle of attack is the sum of the induced angle of attack and the effective angle of attack. So, this relation has to be recollected here, and we have to keep in mind that the CL for any section will be given by 2 pi into alpha effective minus alpha at L equal to 0, assuming this to be thin airfoil section. So, basically what are we trying to say? That if we were to look at the sectional characteristic, then you have alpha L equal to 0 here, you have alpha stall here, you have some other intermediate alpha. This happens to be the effective angle of attack, and if you look at the slope, this slope is given by tan of that angle theta. So, that will be CL by alpha effective minus alpha L equal to 0. Now, if there is no geometric twist along the span, that means the alpha remains same along y, no variation along y, and therefore, at each section of the finite wing, the sum of alpha I plus alpha effective will be the same. Now, alpha I is a function of y. Because as you may recall that alpha I comes up as an integral, and that integral value will change along y. So, alpha I in general is a function of y, thereby alpha effective will also become a function of y. They would be different functions, but they are nevertheless functions of y, and thereby CL will also ultimately become a function of y. Of course, we are assuming that the sectional characteristics are not changing. That means, there is no aerodynamic twist, there are no different airfoil sections that we are deploying along the span wise locations. So, the CL value finally also becomes a function of y in the process, that is what we understand. Now, when we consider the lift per unit span, then we can recall the Kutta-Joukowski's theorem, and at that span wise location we can use the value of gamma to obtain the lift per unit span using the Kutta-Joukowski's theorem. We can use that to calculate the sectional lift coefficients or lift coefficient also. This is how you will calculate it. So, at y equal to y naught, if you are taking the section, then what happens is you find out the CL at y naught times q infinity into C at y naught, that is if the wing has taper, this will not be a constant anymore, it will be a function of y. So, at y naught this is how it will work out. So, let us write it as lift per unit span at y naught, and from Kutta-Joukowski's theorem it will be working out like this. So, what does it give us? The CL at y naught will be found to be 2 gamma at y naught by u infinity C y naught. If you just rearrange this equation. So, CL at y naught again is by definition 2 pi alpha effective at y naught minus alpha L equal to 0 at y naught. We have seen this earlier. So, the alpha effective at y naught will be finally gamma at y naught by pi u infinity c y naught plus alpha L equal to 0 at y naught. So, alpha y naught is 1 by 4 pi u infinity minus b by 2 to b by 2 d gamma dy into dy by y naught minus y plus gamma y naught by pi u infinity c y naught plus alpha L equal to 0 at y naught. This is the contribution coming from alpha I, which we have already derived. This is the contribution which is coming from alpha effective, which we just looked at. This basically gives you the Prandtl's lifting line theory. Basically, it just says that the geometric angle of attack is a summation of the induced angle of attack and the effective angle of attack, but by assuming a continuous distribution of gamma along the lifting line, it has been represented in the form of a distribution of gamma, and it is actually an integro differential equation in gamma y. Because you have a derivative, again you have an integration. So, we have now come up to the Prandtl's lifting line theory. Now, let us see how we can take it forward from here. How can you utilize this theory further in order to define the aerodynamic characteristics of a finite wing? When we look at it from the Prandtl's lifting line theory point of view. So, what we are basically talking about is that if we do have a solution of the gamma as a function of y, then using that solution from the previous equation that we defined, if we can solve it and we can obtain gamma y, then using that solution what all can we do? So, the lift per unit span, again we recall, is defined like this when you are defining it about the point y naught. So, based on this expression, the total lift, so let us define this as lift per unit span. The total lift, let us call it as L total, will be an integrated effect of this over the entire span. So, that will be gamma y dy, and from the L total you should be able to get the C L, minded that this is capital C, because you are talking about the 3-dimensional body. That will be L total by q infinity S. This is the wing planform area. So, that boils down to 2 by u infinity S minus b by 2 to b by 2 gamma y dy. So, this is how you would be able to obtain the total lift and the lift coefficient. Can you estimate the induced drag? Let us see. So, induced drag is given by L sin alpha I. For small alpha, obviously this can be approximately L alpha I, and we are talking about it in the per unit span basis. So, that can be written as rho infinity u infinity gamma y naught alpha I u y naught again. So, that will be your d I at y naught per unit span, and then you get the total induced drag by integrating it, similar to what you did for lift. So, the total induced drag will come out to be rho infinity u infinity minus b by 2 to b by 2 gamma y alpha I y dy. So, the y variations of gamma and the induced angle of attack, everything get into that integral. And once you are able to do that, similar to what you did for lift, you can obtain the induced drag coefficient, again a capital here because it is a 3D body, di by u infinity s, which finally becomes 2 by u infinity s minus b by 2 to b by 2 gamma y alpha I y dy. This is how the induced drag will be estimated. Now, can we have a very special distribution of gamma y which can be easily integrated? Let us try to propose something. We are proposing an elliptic distribution, an elliptic circulation distribution. Is it consistent? Let us try to figure out. So, at y equal to plus or minus b by 2, you will find that the gamma will go to 0, which should be the case because the edges of the wing should not be producing any lift, and therefore, the gamma should be 0. At y equal to 0, on the other hand, you get the maximum value of gamma, that is the peak value, which will turn out to be gamma 0. So, this seems to be a rational distribution. So, if this distribution is used, then how does the downwash come out? For obtaining the downwash, you have to work out the d gamma dy, because the downwash expression looks like this. So, using this gamma distribution, you have to find out the y derivative, but working out this in this plane will be difficult. So, we usually use a transformation like this. So, y is written as b by 2 cos theta. So, we transform it to the theta plane. We do not solve it in y. So, dy becomes minus b by 2 sin theta d theta. Similarly, the limits would change, and therefore, the integral finally looks different from what you have here in terms of y. The integral will look somewhat like this. Once you transform it, it will look more like this, minus gamma naught by 2 pi b. Look at the limits of integration, it changes from 0 to pi cos theta d theta by cos theta minus cos theta naught. Remember that theta naught corresponds to y naught, theta corresponds to y. This is the mapping. So, in order to work this out, we need to use a standard result. Let us write down that result here. So, if you were working out this integral, it will come out to be pi sin n theta naught by sin theta naught. Now, in this case, our n is equal to 1, and therefore, it is very simple. It turns out to be pi, and therefore, your final expression comes out to be gamma naught 2 by 2 pi b into pi, which is minus gamma naught by 2 b. So, what we have finally is, so this is w, mind it. Now, in terms of theta, so you are actually expressing it at theta naught basically. So, the w turns out to be minus gamma naught by 2 b, which is basically a constant. That means, it does not have any span wise variation, it is constant all over. So, if you were to plot the w along the span of the wing, everywhere it remains constant. While if you plot the circulation, it varies like this. It has an elliptic nature. This is w, this is gamma. This is the appearance. What about induced angle of attack? Can we work it out? Alpha I. So, that is what? That is minus w by u infinity. It is very simple because we have a constant value of w. So, the alpha I comes out to be this, which is also constant. That means, induced angle of attack is the same all over along the span of the wing. Now, look at this result. You can see that if the span of the wing is increased, it is made larger and larger. When it goes to infinity, alpha I tends to 0. That means, there is no induced angle of attack at all. Also, if you were to look at the w expression, there is a b in the denominator. So, the w will also tend to 0. There is no downwash. That means, the induced drag effect will go away completely for infinite wingspan. That means, when you look at aerodynamic efficiency, the most efficient one is the infinite one, but in the real world we cannot use that. We have to use configurations with finite span. Therefore, we have to make a compromise. Can we express alpha I in terms of the CL for the wing and the aspect ratio of the wing? Let us try to answer this question. So, we again start from the lift expression and we work out that the lift for this wing will come out to be pi b gamma naught rho infinity u infinity by 4. I leave it as a homework exercise for you to try out integrating the lift per unit span expression by using the gamma that we have proposed, the elliptic distribution, and you should be able to integrate and get this result. So, this is the expression for lift, and then from here you can obtain the expression for gamma naught, which will turn out to be this. Again, we remember that L by definition is CL into Q infinity into S, and therefore, if you plug that in into this equation, you will finally come up with the expression that gamma naught is equal to 2 CL u infinity S by pi b. What about the induced angle of attack? Induced angle of attack is gamma naught by 2 b u infinity, which is nothing but 2 CL u infinity S by pi b into 2 b u infinity. And then once you work out, it will come out to be this CL by pi AR, AR being the aspect ratio of the wing, which by definition is b square by S. That means, the induced angle of attack comes out to be CL by pi AR. Again, it is clear from here that if the aspect ratio becomes infinitely large, alpha I will tend to 0. Also, alpha I will increase as the CL increases. You may like to express the induced drag in the form of a coefficient. So, the induced drag coefficient will come out to be CL square by pi a r. How do we do it? Of course, the induced drag coefficient by definition will be 2 by u infinity s integration minus b by 2 to b by 2. What do we integrate? We integrate gamma y alpha I y dy, and remember that we have a comfortable situation, the alpha I is a constant here, and therefore, it will come out of the integral. Additionally, you need to see that integral gamma y dy in this case will come out to be pi gamma naught b by 4. So, when you plug these things together, you will be able to come up with this expression, that C d I is C L square by pi a r. So, once again, at high values of C L, C d I is going to be large. When does that happen? During takeoff and landing, we have discussed that the aircraft deploys high lift devices, the lift is large, and therefore, obviously, the induced drag will be large. Again, if the aspect ratio is small, the C d I again will be large. So, these are lessons that we have to keep in mind. Again, with the elliptic distribution of lift, we can also show that the chord length C y has an elliptic distribution. So, this is again something that you can explore on your own and try to work it out at home. So, we first looked at Prandtl's lifting line theory, then we looked at a particular special case of an elliptic lift distribution. We can have a more general lift distribution by taking the lessons from what we already learned. So, in the elliptic lift distribution, when you express it in the theta plane, that happens to be gamma naught sin theta. The same thing as a function of y was this, we recall that. So, that in the theta plane would look like this. So, there is a gamma naught with a sine term. So, if we are looking for a more general lift distribution, why should we look for that? We may look at more arbitrary wing planform geometries, where the chord variation is not elliptic, it may be more complicated. We are also not looking at a very simple geometry like a rectangular wing, for example, because that is not going to give us a very superior aerodynamic performance. So, we may have a very typical C y distribution, which is not fitting into these frameworks, and therefore, we need a more general framework, where for arbitrary planforms we should be able to work out this gamma distribution. So, the rational way ahead in that case would be to use a series expression. So, we can use a Fourier sine series instead of just using one term, like was used in an elliptic distribution. So, how can that series look like? Maybe defined like this. We can have typically capital N number of terms where n is not too large, and therefore, a finite Fourier series. So, in that case we can say that how will Prandtl lifting line theory work out? The Prandtl lifting line theory expression will work out to be a more generic one, and without going into the details of that, we are just stating it straight away that the sum total effect of this kind of a model will give you an expression for alpha at theta naught in this form. So, from the Prandtl's lifting line theory expression, you can see that there is slight variation here because of a more general distribution. So, this would be sin theta naught. So, this is the Prandtl's lifting line theory for a general lift distribution. So, in this lecture we discussed further about Prandtl's lifting line theory. We first developed the framework of the theory, then we applied it to a special case, that is for the elliptic lift distribution, and then we also looked at a general distribution, and we will take this theory forward in the next lecture. Thank you.